All right, today we're going to talk about moles, which is how we measure chemical quantities in chemistry class. Up to this point, you learned about factor label method, and we learned factor label method so we could do mole calculations. To start today, let's talk about the basics of moles. So a mole is going to be a number, and specifically it's the number of atoms in 12 grams of carbon-12 isotope. So it's a standardized number. This happens to be a very, very large number, 6.02 times 10 to the 23rd, and it's also known as Avogadro's number. He was fundamental in figuring out this value. Like the number dozen, which is 12 items, a mole just means this big number, 6.02 times 10 to the 23rd. So we can make an equivalent statement using that fact. There are a number of different molar conversions, though, that we can use. Besides the 1 mole is equal to 6.02 times 10 to the 23rd particles, we have some others. Notice that I was talking about moles, M-O-L-E, earlier, but I have in my conversion M-O-L. This is the abbreviation for mole. You save a lot of ink by not writing that E. So 1 mole is equal to 6.02 times 10 to the 23rd particles. And for chemistry class, it's normally atoms, ions, or molecules, but it could be something like shoes or pens or markers or whatever item that you can possibly count. That's what we would use this fact for. We also have 1 mole is equal to 22.4 liters of gas, and this is measured at STP, standard temperature and pressure. When we do these problems in class, we will always have values provided to you in STP, at least when we initially do these problems. Finally, 1 mole is equal to the molar mass in grams. And this one's really useful because we can't measure out individual atoms, but we can measure masses of substances, and then we can infer how many particles we have, and that number of particles is useful for figuring out how much reaction will occur and how much product will form, etc., etc. All of these equivalent statements can be used to write reciprocal fractions as conversion factors, just like we did when we learned factor label method. Another way to graphically look at those same facts that we just looked at is something called molehill, where 1 mole is at the top, and then there's 3 pathways to travel up and down molehill. Notice that you cannot travel from grams to liters directly. You need to instead go from grams up to moles, moles down to liters. And then if we're using molehill, each one of these lines would represent a line in our factor label grid setup. Same information, just a graphical way to understand those equivalent statements. So one of the equivalent statements was 1 mole is equal to the molar mass in grams. So how do you figure out molar mass? Well, each substance is going to have its own unique molar mass, and you can figure that out by using the periodic table, and you'll add up the atomic masses of all the substances that we happen to have. So for example, if we had lead 2 nitrate, that's what this formula's name is, we would say, well, there's 1 copy of lead because there's no subscript on lead, and then for the nitrate, there's N, but then on the outside, this 2 distributes to both of these atoms, so there's 2 copies of N, and then there's 2 times 3, which makes 6 copies of O. So how we use the periodic table to determine the molar mass is we find the element that we're looking for, so in this case lead. I'm going to find it on the periodic table, and I can see that lead has a molar mass of 207.19. So I'm just going to write that this is 207.19, and what this means is that 1 mole of lead weighs 207.19 grams. If I was just to say what's the molar mass in grams of lead, I would do this number and then write my unit as grams per mole. For a compound, I have to do a little bit more work, but I'm going to use the same principle. I'm going to use the atomic masses of each of the atoms. So lead weighs, again, 207.19. There's only 1 copy because there's no subscript. So I'm going to look up nitrogen. And if I look at nitrogen, it weighs 1401. So plus 14.01. But then there's 2 copies because the 2 gets distributed into the 3 and to the N. Plus oxygen's mass. And if you look on the periodic, oxygen weighs 16.00 times, this time it's 2 times 3, which gives me 6. Now if I just do this math, add the three values together, my number will end up being 331.21, and this is grams is equal to 1 mole, or 331.21 grams per mole if you don't write it with an equality. Now we use those values when we're trying to do factor label, as if we're going to be using the molar mass in grams, and if we're going to set up fractions. So we're going to solve these factor label problems the same way that we solved factor label problems in the past. We need to identify what we know. We're going to do that by writing a K above that number and value inside the text of the problem, or if you just have a lot of white space, you could do K equals. And then also what you don't know, put a question mark above that unit that you're trying to solve for. Start with what you know, put it in the top left box, and then make your units cancel by putting them opposite. So if I'm doing work over here, this is my problem. What I know goes into my top left unit. So if this is grams, I need to put grams again on the bottom, and then grams are equal to 1 mole, so moles goes on the top. And if I'm solving for atoms or something like that, I need to make moles go away, and then atoms would be on the top, and I'd use my appropriate number. So what you should have learned after watching this video is that 1 mole is a quantity just like a dozen, and it's equal to 6.02 times 10 to the 23rd, Avogadro's number. You should have learned the other conversion values, that 1 mole is equal to 22.4 liters of gas at standard temperature and pressure, and that 1 mole is equal to the molar mass in grams of a substance. After that, you should know how to use the periodic table to determine the molar mass in grams of a substance, and you should also know how to set up a factor label problem using these mole values. Hope that helps.